So no interesting information. Nothing interesting in this problem. The set, the phase space, the unit interval, it happens to have integer dimension 1, but it's a fractal with dimension 1, like in a trivial way. It's not doing anything. On the other hand, if rho is not equal to a constant, you have interesting things happening. So let's look at the case where, for instance, the logistic map. That was a non-trivial case. So you had rho of x equal to 1 over pi times square root of x times 1 minus x. And I need to put that in here and ask, what's this guy going to do? And take the limit, etc. So if I do that, in this problem, it's equal to n pi 1 over square root of j minus half over n, 1 minus j minus half over n, and this whole guy raised to the power q, and then I have this. By the way, let's just write this as log n to the power 1 minus q. I have to do this. So as you can see, this summation is a Riemann sum. So it's essentially an integration which will tell you it's dx over square root of x times 1 minus x to the power q between 0 and 1. With suitable n's and so on, I can convert it to this. But at what stage is this integral convergent? Now this is not the probability density, it's the density raised to the power q. So we have to worry about the convergence of this integral. And it's got singularities at 0 and 1. And the singularity becomes non-integrable if this exponent exceeds 1. Right? So divergent for q over 2 square root greater than 1, which means q greater than 2. And equal to, then it's logarithmically divergent. For q less than 2, I'm okay. For q greater than q 2, I'm in trouble. For q less than 2, I can take this, go back to the integral altogether, and write this as n to the power minus q times this fellow here. I put a 1 over n outside and an n out there, so log n to the 1 minus q times this fellow. And this thing here goes to this integral in the limit n tends to infinity. This cancels against that, the log adds up. So this answer goes to 1 plus the finite number, this integral, divided by log n. And that goes to 0. So we come to the conclusion that dq equal to 1 for q less than 2. But for q greater than 2, you've got to worry about what this Riemann sum is. You have to smooth this integral by converting it to a Riemann sum and then actually doing the Riemann sum. Now that's not very hard to do because it's exactly the same argument as before, except I can't take it out as an integral. So this is log summation of the n j equal to 1 to n, this guy. And remember there was an n pi. There was an n pi. Now this pi factor I take out and take its log, divide by log n, everything goes to 0, so that's irrelevant in the limit. And I have this guy, and let's move this n in. That cancels this and makes this n. N minus j plus half to the power q. Now look at all these guys here. If j is near 0, near 1, then this is of order n to the minus q over 2. If j is near the other end, n, then this factor is of the form n to the minus q over 2.
Right? You are moving in an n inside a square root.
Yeah, I had n, so I have to multiply this by, so it's n squared inside. One n cancels here, one n cancels there. And it gives this. Now my argument is, in this big sum from 1 to n, those terms near j equal to 1, the beginning, are going to go like n to the minus q over 2. Those near the other end are going to go like n to the power minus q over 2 again, because of the other bracket. The fellows in the middle, j of the order of n over 2, are going to go to 0 even faster, like n to the minus q. So certainly in the limit, the large terms will dominate, and you will end up with an answer which is equal to log n to the minus q over 2 over log n to the 1 minus q. So this thing here is equal to q over twice q minus 1 for q greater than equal to 2. So what it says is that you have a non-trivial answer now, and it says there's a sort of phase transition. This dq is like a free energy. You've taken some measure and you've taken the qth power and you're finding the log of this whole fellow. So you plot q here versus dq. For all q less than 2, it remains at the value 1 till you hit the value 2, and then it starts dropping, and as q tends to infinity, it tends to a half. So you have this behavior. That's reminiscent of the phase transition. This free energy has a cusp at this point. And now you can take the Legendre transform of this and go from the Helmholtz to the Gibbs and so on. That's called the F alpha spectrum. And there's a huge amount of huge industry studying this sort of thing. Do this same argument for the cusp map. It's easier to do because that doesn't have these square roots. There the rho of x was equal to 1 minus x over 2. And you have to take integral to the power q from minus 1 to 1. Where will this fellow diverge? Where will this integral diverge? It will diverge at this point if q is less than minus 1, less than equal to minus 1. So the phase transition in this problem will happen at q less than equal to minus 1. And to the right of it, it's got another functional form. So I leave you to find this thing here. And the picture here will look like till minus 1, it will come down from some value, and then after that, it goes up. This is what we do. In fact, if this density, this is the last thing I'm going to say, if this density goes like some x minus a to the power alpha over x minus b to the power beta, so that you allow for both positive and negative powers, and alpha beta are positive, beta greater than minus 1, so you don't have divergence. The interval is from a to b, then the dq, and this is an exercise, show that as a function of q, there's going to be a phase transition due to the endpoint singularity at a if alpha is less than minus 1. And remember, this whole thing is raised to the power q. So if q alpha is less than minus 1, you have a problem. So there will be a phase transition at minus 1 over alpha. Below that, it will have some other behavior. And then similarly, beta q must be less than 2, less than 1. So q must be less than 1 over beta. So at 1 over beta, there will be another transition. And so you have to show that this thing comes like this, remains constant, and does this. And the asymptotic value here, if I remember right, is 1 plus alpha, and the asymptotic value here is 1 minus q. That's what the dq does. So that's an exercise to show that. You have to be careful with these Riemann sums, etc. Then you can find all the points of non-analyticity of this free energy. Yeah. 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 It just says no. I mean, it's like the behavior of, yeah, there's no significance. Yeah, yeah. But it's still finite. I mean, that's the whole point. In these maps, in these systems, the dq is finite as q tends to infinity. Coincidentally, you can show rigorously that, there are convexity theorems. There are theorems like the free energy. You can show that if q prime is greater than q, then dq prime is less than equal to q. So you have a whole host of theorems of this kind, which you can show. It's like the convexity property of the free energy. So the fact that dq has a finite limit on both sides is an artifact of the models we are looking at. This is in more general cases, need not always be the case. And then this is the sort of starting point of understanding dynamical systems. Then what one does is, in a real system, you do symbolic dynamics, try to reconstruct as much as possible. From a given time series, you reconstruct the full dynamics by what's called an embedding dimension, etc., etc. Big, huge literature on this. I haven't had time to touch on any of those things. But this is just to show you, just a last statement to show you that classical dynamics has an enormously rich structure. Not just the Hamiltonian dynamics, which already has a rich mathematical structure, but more general systems, dynamical systems, even guided by first-order differential equations, have an incredibly complex structure already. So the moral of the story, I think, is that differential equations may look very simple, or functional difference equations may look very simple. The rules may be very simple looking. The actual solution space may be incredibly complex. And our job is to try to put some order into this complication. And all these methods are ultimately methods to try to bring some kind of semblance of order into this, in the sense that how do we understand really complex dynamics by combining probabilistic methods, stochastic methods, etc., along with techniques from calculus and measure theory and so on. So roughly that's the endeavor of dynamical systems. And the subject is very rich, extremely rich. Huge number of problems are open problems. Even problems which look very obvious, very simple. Many of them are still open. So there's a lot of room for new research in this. So that's, I guess.
All set of differential equations can be written as the z dot equal to fj.
As the?
Z dot equal to
That's
fj.
a good question. He says, can you take any general differential equation, ordinary differential equation, and nth order differential equation, and one variable, and write it as n for coupled first order equations? The answer is yes. Just define the successive derivatives as new variables. But if you give me an nth order differential equation in one scalar variable, there's no guarantee that I can decouple it and write it as n first order differential equation. Fortunately for us, in dynamical systems, you're given this alternative, what you're generally given is a set of first order differential equations already as a simple model. Rarely do you have a higher order differential equation to start with as a model. You always construct it from first order differential equations by identifying the right number of variables. So in that sense, we are fortunate. But the problem is actually a tractable one.
And the other thing is that, according to you, how does fixed point differs from critical point?
Well, I use the term critical point when the vector field on the right hand side in a differential equation, when the phase space velocity was 0, when the vector field was 0. I use the term fixed point when the right hand side in a difference equation was 0 automatically, because that is the fixed point of the map. On the other hand, in the differential equation case, it's the derivatives that vanish. Here it's the variable itself, which is equal to itself. It doesn't change. So that's why I distinguish between the two.
Thanks.
So it's time for this. Announcements. One is this. So first announcement is the last lecture will be in the. We will not be here. Will be in the same place where we were at the banquet yesterday. So that's in the library block, first floor. There is a seminar room, so it will be there.